Okay, a number of times I've been using drawing free body diagrams and ignoring the gravity. So what I'm going to do here is demonstrate why it is that you can ignore gravity by doing a simple example and including the gravity term. So what I've done over here is I've got a mass with a spring, and I'm including the gravity term on here. Now, what I'm doing is I'm defining the free length of the spring as L0, and if nothing was touching the spring would be located at this point right here. Then what I'm going to do is I'm going to attach the mass, and I'm very slowly going to ease the mass down until it sets still, and so that's called static equilibrium. And when you do that, the mass is going to move down a little bit and then stop at some point. And so I'm going to draw a line, this blue line there, that is coincident with the top of the mass when the mass is sitting still. That's called the static equilibrium point, and that is a constant. Because gravity is constant, mass is constant, all that. So that is where it would set if it was minding its own business. And then from then, I'm going to measure where the mass is by this variable x. And x is going to be 0 if the top of the mass happens to be at the line of the static equilibrium point. So then what I do is I'm going to draw a free body diagram of the mass when it's at rest. And so I have a spring force pulling up, and the spring is equal to the spring constant times the deformation, or the stretch in the spring. The stretch is this distance d, because the spring is L0 plus d, and then you subtract off the free length, you're going to end up with the stretch of d. And then you include the mg pointed down. And then here then you have this equation for the the static equilibrium point. So you can find an easy formula for the distance d in terms of the gravity. Then over here in the blue, I'm drawing a free body diagram of when it is moving. And so I use the same steps that I did, I've always done, for the spring. And so this term right here is the total length of the spring, and I don't know why, but this should be an x right here. So the spring is L0 plus d plus x. That's how long the spring is, and then I simply subtract off the L0, and that's how far it has been stretched or deformed. So that is the equation for the spring force when you include the free length and everything in it. And I also include the mg in my free body diagram, which normally I ignore. Okay, so then you're going to sum forces. So here is the summation of forces on this device, and the reason it's k times x plus d is because you have an L0 here and you're subtracting L0, so that one's gone, so you're left with just the x plus d. And then over here, what I'm trying to show is that I'm taking the second derivative of the motion, right? And so I'm including everything, free length and the whole bit. The point though is that this term L0 and the term d, those are constants, and so when you take derivatives, they're going to disappear, and all you're left with is the second derivative of x. Okay, so now on the left hand side you have mg minus kd minus kx, but you can see from this point up here, from this equation, that mg and kd are equal. So these two terms right here are equal to 0, so they cancel out. And what you're left with is the equation that you would have if you were just ignoring this completely. So this equation then is exactly what you would have if you just started out by ignoring gravity. Now in the next problem that's down here, I'm doing one to demonstrate that there are times when you do have to include gravity. What I have here is a mass attached to a string, and the string is tied to a point, a rotation point. And it's 1 degree of freedom, and the variable is theta. So if I tell you theta, you know where the mass is, so it's 1 degree of freedom. Because the theta is positive in the counterclockwise direction, I'm choosing positive direction to be counterclockwise here. The free body diagram, I'm cheating a little bit, but here's the tension that's in the string, and here's the gravity that's acting on the mass. So when you have rotating objects, which is what this is, rather than writing F equals ma, you typically write summation of moments. When you write summation of moments, you are allowed to write summation of moments around fixed points or around centers of mass. In this particular case, I'm writing the summation of moments around this rotation for the end of the string. So because the tension here passes through the point that you're summing moments around, it has no moment. But the gravity term does have a moment. It's equal to the magnitude of the force times the perpendicular distance, which is the moment arm. So this is the perpendicular distance. It's this distance right here. So that is the moment. And because the moment's producing a negative, you have a negative sign in front. And the summation of moments then is equal to moment of inertia, that's the mass moment of inertia, don't confuse it with the complex number, times the angular acceleration of the object. So in a case like this, you can see that if you were to ignore the gravity, you would not get a valid equation. If you ignored gravity, you'd have 0 equals I theta double dot, and you'd conclude that theta double dot was constant, which means that it would have a constant velocity, which is not true. Now, the conclusion is if gravity is causing the oscillations, then you have to include the gravity in the free body diagram. If gravity is not causing the oscillations, then you do not have to include it. And so, for example, down here, this problem right here, gravity was causing the oscillation, and you have to include it. And this problem up here, gravity is not causing the oscillation, and it wasn't necessary to include the gravity. Whenever you are in doubt, you can include gravity, and if it is supposed to cancel out, it will. What you have to be careful of is to make sure that you include the free links and the static equilibrium points and all of that in order to have it work out. So the conclusion is include gravity when it causes the oscillation. You can exclude gravity and measure from static equilibrium when it doesn't.